All right, hello everyone, and welcome to my channel. This is a channel for educational purposes. We look at theories of everything in depth and, just try to show you what they're all about. Things that you've never heard of before, most likely, because they've been suppressed, probably because of their success and their threat to the science that's out there. And today is our 471st video on the reciprocal system of theory from Dewey B. Larson. Larson proposed his two fundamental postulates in 1959. Just two sentences about how he believed the universe operated. And then from there, he derived a theoretical universe about what the universe would look like if his postulates were correct. I went over that in about 15 videos over a year ago called The Outline of the Deductive Development of the Reciprocal System, which you can take a look at if you're curious how he derived this theoretical universe. But once he did derive the theoretical universe, he compared it with the empirical, already measured universe of the legacy scientists that they had compiled in their tables from laboratory and observatory work. And we're looking at one of his books here called Basic Properties of Matter, which is primarily on chemistry, that is an examination of Larson arriving at equations for the basic properties of matter, such as, the melting point and the specific heat and the compressibility, and then comparing them with the scientific tables. We're in chapter 8 of that book called Thermal Expansion. And we'll get to that a little later, but let's go through some of the basics of the reciprocal system. Guess we'll start with the postulates. Larson's reciprocal system is otherwise known as the universe of motion. That's the name of one of his books on astronomy, Universe of Motion. And the reason is because he is, I guess, one of the few scientists to attempt to construct his universe upon motion, as opposed to matter or maybe in the 20th century energy, or even force, the four fundamental forces. But Larson constructs his universe on motion, and in particular, he's referring to a kind of motion that he calls scalar motion. This is a motion with a magnitude, but no specific direction. You can envision a scalar motion using a balloon that you put dots on. And if you blow up the balloon, all the dots will be moving away from each other. And they won't be moving in any specific direction. Every dot will be moving in every direction. Every dot will be moving away from every other dot. And indeed, every dot will be moving away from every location on that balloon. And if you contract the balloon, they will all be moving toward each other. Larson refers to that outward motion as the progression, and the inward motion as gravitation. So scalar motion has a direction, either out or in, but no specific direction. And from there, Larson, puts together his first postulate, and his first postulate is where that's where his theory is laid out. And in the second postulate, Those are basically the laws of the universe that most scientists would accept, at least, in if not in principle, in practice. And he uses the second postulate in order to derive the theoretical universe from the first postulate. So the first postulate is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Now, we could split hairs and disagree with the kind of geometry or the kind of mathematics that Larson's using, but the general idea is that he's going to be using mathematics and geometry along with logic to take his first postulate and from it deduce a theoretical universe. So let's look at that first postulate. There's really 4 prongs of it. The universe is composed of motion entirely. Again, we said that that is a scalar motion. Now, this is, you've got to, in order to accept the universe of motion, you have to be able to accept the concept of motion without anything moving. Motion precedes anything that might be moving. And indeed, motion comprises anything that might be moving. So motion is primary. So you can have an empty universe that is in motion. And that is really what the progression is. The progression is an empty universe progressing outward in all directions. And we'll see that it is progressing at a certain speed. But, okay, so that's the first prong. Then we also have that the universe is made out of motion. Motion is the relationship between space and time. There are 2 reciprocal aspects. Space and time do not have any independent existence. They only exist together in motion. And motion is basically a fraction, with space or time as the numerator and time or space as the denominator. And you can see that with speed. Speed is space over time. The bike is moving 10 miles per hour, 10 miles of space and 1 hour of time. But Larson spreads that out to all forms of motion, which he refers to all forms of scientific phenomena as forms of motion. So matter is a form of motion. Energy is a form of motion. Force is a form of motion. Pressure is a form of motion. Acceleration is a form of motion. Magnetic flux is a form of motion. Electrical capacitance is a force of motion. And they all have their time-space signatures. So like speed is space over time, energy is the inverse of that, time over space, Larson finds. Larson also finds that matter is time to the 3rd power over space to the 3rd power. So every kind of motion has its own time over space or space over time signature. Now, one other obstacle or sticking point that is prevalent with trying to understand the reciprocal system is adopting the container viewpoint. And the container viewpoint basically will lead you to stationary reference system, or to stationary reference system. And the container viewpoint is that we is, what we've had as a common denominator in Western civilization for thousands of years, that space and time are the background that we move through as we go through our universal drama. So space is this three-dimensional thing that is still, and we move through space and events unfold in time. But in Larson's universe, space, time, and motion are the contents of the universe. Motion, the universe is composed entirely of motion, and motion is the relationship between space and time. So the universe is composed of motion, not of something else, matter or energy, moving through space and time. The universe itself is composed of space and time. So we have to be able to put aside that container viewpoint and get with the contents viewpoint. Now, the container viewpoint persists in a little bit in abstraction in the reciprocal system and in the stationary reference systems. So, this 3 dimensions of space in a still frame, and time unfolding or progressing or always getting later and later is what Larson refers to as the spatial reference system. 3 dimensions of space and progressing time. So time is still moving in a scalar manner, but space has become abstracted, or what we would say gravitated. It has stopped. Time is still progressing, but space has stopped and has become 3-dimensional and, like a background. And this is the what Larson calls the stationary spatial reference system. And then, since time and space are reciprocals of one another, there would also theoretically be a temporal reference system where we have 3 dimensions of time and clock space, coordinate time and clock space, where space is still progressing. Space is getting farther and farther and farther apart, like on the surface of an expanding balloon, but in no particular direction. And time has stopped. And time is now in 3 dimensions, 3 coordinate dimensions, x-like, y-like, and z-like coordinates, analogous to the x, y, z coordinates of the stationary space. So Larson refers to that as your temporal reference system. So you got one reference system with 3 dimensions of space and scalar time, and one with 3 dimensions of time and scalar space. This complies with the space, time, and motion come in 3 dimensions, part of that first postulate. But space, time, and motion, 3 dimensions of space, are needed just to express 1 dimension of motion. Motion goes beyond 3 dimensions of motion, go beyond that, either the spatial reference system or the temporal reference system. Neither one of those reference systems are sufficient to express 3 dimensions of motion. And I guess for that, Larson is using what he calls the natural reference system, which is the progression with some of this discrete unit postulate thrown in. Discrete unit postulate, space, time, and motion come only in discrete units. And so the progression is this outward motion of space and time in all directions, from all locations, at all times, omnipresent and eternal. But that motion is at a certain speed. It is at unit speed. All of our scientific phenomena come in units. They are quantized. They have different levels, 1, 2, 3, 4, 5. There aren't like decimal points or fractions between them. They come in levels. Now, if you look at the inverse of that, then you do have fractions, 1 over 1, 1 over 2, 1 over 3, 1 over 4. But that is really when you are inverting it, and the real measure of it is the 1, 2, 3, 4, 5. But you can't have something like 3.62 or something. That would revert to the 3. And so the progression is occurring at unit speed. And unit speed is 1 unit of space per 1 unit of time, which is what Larson calls unit speed. So the progression of the natural reference system, as opposed to the spatial reference system and the temporal reference system. The natural reference system is a moving reference system. It's a reference system in motion, which makes sense in a universe of motion. And it is progressing from all locations at all times in all directions at the rate of 1 unit of space per 1 unit of time, which is also known as the speed of light. So this progression of the natural reference system is the midpoint of the universe, the null point, or the condition of rest of the universe is to be in motion at that rate. And that means that half the universe is moving actually faster than light. Half is moving slower. Larson refers to these as the cosmic sector and the material sector, respectively. And they are reciprocals. In the material sector, you have coordinate space and clock time. In the spatial reference system. In the material sector, you have the temporal reference system, coordinate time and clock space. When you cross that unit speed boundary, you have to invert the rules. You have to invert the roles of space and time. And then within both the material and cosmic sectors, you have a subregion or an inside region within a unit of space or time, because of the discrete unit postulate again. You have to have a full unit. And so when you have something like a molecule or atoms or molecules that approach each other to just 1 unit of space or 1 unit of time, in the case of cosmic atoms and cosmic molecules, then they can't approach each other any closer. And so if they get to be 1 unit of space apart, they can't get any closer. So what they do is they move further out in time instead of space. And since time and space are reciprocals, that is the equivalence of them moving further in space. And we see it as being inward in space because we only see space. We can't see time from our vantage point in a stationary reference system because we are gravitationally bound to that system. And so we see it in what Larson calls equivalent space, but it's really happening in time. That is what Larson calls the time region. Inside 1 unit of space is what he calls this three-dimensional time region. And when we look into equivalent space, what we see is basically distorted. in a couple of different ways by our inability to kind of see across that boundary. Also, once we cross that boundary, the rules reverse again, and the progression is now moving inward, and gravitation is moving outward. And there is an equilibrium that is established also between particles moving inward and outward, which we see as between pressure and temperature. And that equilibrium is called the interatomic distance, and that is because the progression is constant, omnipresent and eternal, and gravitation is variable. So there is a point where they are the same, and that is what Larson calls the interatomic distance, and that is really occurring at, I guess, zero temperature. And then atoms and molecules are basically formed from reversing that progression of the natural reference system, which is the source of everything, reversing that outward motion of the expanding balloon to the inward motion of the contracting balloon, which is gravitation. Gravitation is inherent to all matter, and it is accomplished by reversing the progression in 3 dimensions. Again, you got to remember that motion is in 3 dimensions, so that progression, while that is analogous to the scalar motion that we're talking about, that scalar motion occurs in 3 dimensions. And so matter has to be reversed in 3 dimensions. The first one of which, the 3 dimensions make up Larson's periodic table. So every element of Larson's periodic table has 3 numbers that comprise the backwards rotations that are needed to reverse that progression and turn it into gravitation. Now, the first reversal is called the photon, and then there are 3 subsequent reversals. Larson uses those 3 numbers in order to determine his basic properties of matter. And so we'll start here. Basically, what he just said last time is that we have 0 temperature at that point, that interatomic distance point that I was talking about, where the gravitation, or what you would call thermal motion, or where gravitation equals the progression. And then from that point, gravitation manifests as thermal motion or heat, whereas the progression manifests as pressure and or compression, and is an inward force, whereas the gravitation is an outward force. And then as the more and more heat is added, the body expands, the volume expands, and eventually it gets to what you would call the melting point, because this is the solid state of it. The interatomic distance occurs at 0 temperature. And then so we're in the solid state, but then as it is heated up, it gets to the melting point. At that melting point, again, the thermal motion is in equilibrium with the inward progression of the natural reference system, or the compression. And this is quoting Larson here. This is the point at which the thermal motion is able to cross the time region boundary. The time region boundary is where the melting point is, for all intents and purposes. The melting point is basically, the solid state is 3 dimensions in the time region. The liquid state is 1 dimension outside of the time region, and the other 2 still in the time region. The gaseous state is all 3 dimensions outside the time region. So the point at which the thermal motion is able to cross the time region boundary without assistance from gravitation The thermal motion up to the endpoint of the solid state thus adds a volume equal to the initial volume, because the thermal motion is adding that same amount in order to get to the same equilibrium magnitude, the same magnitude as that progression that the original gravitation had. So whatever the size of the interatomic distance was at the zero temperature, it's going to be twice that size at the melting point, except that amount has to be reduced because we are looking into the time region. And like I said, when you look into the time region, things are distorted in two different ways. We see equivalent space as a second power region, and we also only we lose a lot in the translation looking into the time region, and we only see a fraction of what's actually going on. And this is called the interregional ratio. And the interregional ratio is basically 128, but then you have to add, you may have to add for matter. It's 128 for a photon. For a subatomic particle, it's 128 plus 1/9 of 128. And then for an atom, because that's one photon in a subatomic particle, whereas a matter, an atom, has two photons. So then you have to, it's 128 plus 2/9 times 128, which is 1408 over 9, which is 156.44. So that's the factor that you have to multiply, divide that second unit by. So, although I could be wrong about that, because for some reason, I think I am wrong about that. I think that he uses a different factor to reduce the second unit. Let's see where he goes from here. For an understanding of the dimensional relations that are involved, it is necessary to realize that all of the phenomena of the solid state take place inside unit space, distance, in what we have called the time region. The properties of motion in this region were discussed in detail at appropriate points in the earlier volume, Nothing But Motion, which I also recorded over many, many videos, maybe 6 months ago, if you'd like to review that. This discussion will not be repeated here, but a brief review of the general situation with particular reference to the dimensions of motion may be helpful. According to the fundamental postulates of the reciprocal system, space exists only in association with time as motion, and motion exists only in discrete units. From this, it follows that space and time likewise exist only in discrete units. Consequently, any two atoms that are separated by 1 unit of space cannot move any closer together in space, as this would require the existence of fractional units. These atoms may, however, accomplish the equivalent of moving closer together in space by moving outward in time. All motion in the time region, the region inside unit space, is motion of this kind. Motion in time, or equivalent space, rather than motion in actual space. The first unit of thermal motion is a one-dimensional motion in time. Aha! The first unit of thermal motion is a one-dimensional motion in time. And so I think that's a factor that I'm missing here when I was trying to figure this out. Okay, at the transition point T sub 1, this motion has reached the full 1 unit level. As already explained, only half of this unit is physically effective because it's an oscillating motion, or it's an intermittent motion, because thermal motion is a vibratory motion, but it is ineffective in the inward direction because the progression is already maxed out. So so it goes outward, but just kind of one step, and then it stops, and then it goes another step, because it stops because it's actually going inward, but that's ineffective. So it's only moving at half the normal unit it would normally move, the normal rate that it would normally move if it were just moving outward. So half this unit is physically effective. One fully effective unit is required for escape from the time region. And so this is only half the unit. So at T sub 1, it reaches what would be the melting point, except that the motion is cut in half. And so it has to do this again. It has to double that magnitude in order to actually reach the melting point. This is as clarifying for me, if it's not for you anyway. And so hopefully it will rub off on you, or I can help, bring you along if I can get it. One fully effective unit is required for escape from the time region, and the motion therefore enters a second time region unit. In this second unit, a three-dimensional distribution of the motion is possible, for reasons that he explained earlier, which I don't have mastered. But the motion in time that takes place in the time region has only a scalar connection with motion in the region outside unit space, which is motion in space. This is equivalent to a one-dimensional contact. Thus, only one dimension of the three-dimensional time region motion is effective beyond this boundary. Okay, so the fraction that he's using here is 1/8. And then you have to divide that by 2 to get 1/16, because it's only half effective. Okay, so the effective fraction of the motion is 1/8 of 1 unit, or 1/16 of the total 2-unit time region motion. The expansion is proportional to the effective component of the motion, and this means that the volumetric expansion from 0 temperature to the solid endpoint, as measured in the region outside unit space, is also 1/16, or 0.0625 of the initial volume. On a one-dimensional linear basis, this is 0.0205. Okay, I know we're crawling through this, but we got to stick with it, see if we can get it. And thanks for tuning in.